Hi, so this clip's about electric current, and in particular two equations for electric current. I equals delta Q over delta T, which we're quite familiar with, and I equals nAvq, less familiar equation, but it is in most A levels and in the IB. So what's this nAvq and why is it the same as delta Q over delta T? So that's what this clip's about. So let's look at the first equation. Well, the first equation tells us that the current is the rate of flow of charge, is the amount of charge passing per unit time. In other words, it's the charge passing per second. So let's see what that means. Let's imagine a kind of ideal situation of charge carriers moving through a, say for example, through a pipe. So a pipe might look something like that, with charge entering from the left hand side and leaving from the right hand side. And let's suppose we've got small positive charge carriers moving through the pipe. So let's draw a few like that, and let's suppose they're all moving from left to right at the same velocity v. So it's like a beam of charged particles. So it could be like a beam of protons, say for example, like something like at the Large Hadron Collider or something like that. And of course I've only drawn 6 charges, but there might be billions of charges moving through. So to find the current, we need to find the total amount of charge passing per second. So what we could do is pick a point, for example, if I pick point X there, and we could just watch that point for a second and see how much charge passes by. So what we'd really be doing is seeing how much charge passes through that wall in 1 second. Well, if the charges are going all at speed v, or velocity v, from left to right, then that means they're going v meters every second. So in 1 second, all the ones v meters before x, all the charges in a space, v meters to the left of x, all of those charges will pass through the wall. So really what we're talking about is all the charge in that volume there is the charge that will pass through the point x in the wall at x in 1 second, and therefore if I can find that amount of charge, that will give me the current. Remember, the current is the charge per second, the charge passing per second, and so if I can find the number of charged particles in that volume, then I multiply that by Q, that will be the current. So that's what I need to find. Well, we know the size of the volume because if that pipe has a cross-section area A, then I can say, okay, well the volume of that space that I'm trying to find out how many particles are in will be simply A times the length of the space V, because the volume of a cylinder, which is the cross-section area times the length. So the volume I'm looking for is AV, but what's big N? How many charged particles are in there? Well, the answer to that is I can define little n as the charge carrier density. And what that means is that for a particular material, little n will have a different value, and it will tell me the number of charge carriers per unit volume. So what that really means is the number of charge carriers per meter cubed. And then I can express n in terms of little n, because that means that big N must be the number of charge carriers per unit volume times the volume that we're looking at. So I've got an expression for big N, will be nV, but of course I already know that V is a little v, because it's the volume of the cylinder. So I've got the big N is little n A times V, and because my current is nQ, then that means that it's little n AVQ. And I've found that expression that we were looking for at the beginning, and proved that the current can be expressed as nAvq. Remember that little n is the charge carrier density, A is the cross-sectional area of the pipe, and V is the velocity of the particles moving freely through the pipe, and Q is the charge of each charge carrier. Now, of course, in reality, we're very unlikely to have a lovely ideal situation of a pipe with free charges just shooting through all at the same speed v. And in this case, and we worked out just simply the current that was flowing through the pipe. More likely is that we'd be dealing with, say, for example, a metal wire. But in the case of a metal wire, the situation's a bit more tricky and complicated. If I have a current moving through a metal wire from left to right, then that means I must have it connected to some kind of potential difference. So I'll have the left hand side at some positive potential and the right hand side at some negative potential. And in the wire, because it's made of metal, I've obviously got the complication that it's not just an empty space for my charges to flow freely through, but it's a crystalline metal material. So it's made of lots of metallic atoms, all in a lattice. So I'm going to represent those as lattice ions like this, which are fixed and can't move. And they're ions because the outer electrons in a metal, remember, are delocalized. So that's left behind the nucleus with the inner electrons, which is therefore missing one or more electrons, and therefore they're positive ions. And so the delocalized electrons, of course, in a metal are what carry the current. But of course, electrons are negatively charged, so they're going to be moving from right to left. And so they're going to be experiencing an attraction towards the left-hand side, even though the current is said to be moving from left to right, to the right-hand side. But the electrons can't just simply move freely. They're going to keep bouncing into the ions and sort of ricocheting around the place. But they will, of course, eventually kind of make their way through on a kind of crazy path, because they're feeling an overall pull towards the left-hand side. So at any one given time, the electrons are going to be moving in any particular direction. So we have to redefine V in this case as the average rate of progression of the electrons. So V, small v, is the average rate of progression, average velocity of the electrons from right to left, or down the wire. And we just call that the drift velocity. Now that's likely to be a lot smaller than the speed of freely moving charges in a pipe in a vacuum. And but we still can use the same equation, I equals nAvq for a metal wire. It's just that this time n is the density of electrons, so that's the number of electrons per meter squared. A is the cross-sectional area of the wire, but this time v is the drift velocity of the electron, so it's that average rate of progress along the wire, even though they're moving around all over the place. And q, of course, is the charge of an electron, so I could rewrite that nAvE, where of course E is 1.6 times 10 to the minus 19 coulombs. It's worth just noting in this expression how the various terms would affect the current if they changed. And remember that something that affects the current is also an effect on the resistance of the material. So if I had a metal wire and increased, for example, n, you can see that if the charge carrier density went up, then that means the current would also go up. So that would reflect a decrease in resistance. And wires and materials with higher charge carrier densities, higher numbers of free electrons, would have a smaller resistivity due to that. Also, you can see that the cross-sectional area of the wire will have an effect, because if I have a thicker wire, then obviously it makes sense that I'll have a bigger current, and that also reflects a smaller resistance. And we know that large, thick wires have low resistance from resistivity, and also the drift velocity. If the drift velocity is larger, again a bigger current, that means that there's also a smaller resistance. And it's worth remembering that in a metal, an increase in temperature often accompanies an increase in resistance, and we can see why here, because if the temperature increases, then we know that the lattice vibrations increase, so the positive ions are vibrating more, which is going to make it harder for the electrons to go through. And now we can see how that relates to this, that the drift velocity would decrease because they'd take longer to kind of work their way through the wire. So a higher temperature would lead to a lower drift velocity and a higher resistance. Good, so hopefully that explains the connection between I equals delta Q by delta T and I equals nAvq.